Hi, my name is Todd Garner, and my group partners are Mai Dang and Carlos Estevez. I'd like to introduce our project, which is predicting bone fracture risk in women with osteoporosis, a classification modeling approach. Our agenda today is we'll look at the data pre-processing, exploratory data analysis. Mai will take us through objective one, and Carlos will take us through objective two, and then we'll come back to Mai with our conclusion. So let's dig in. Data pre-processing. Let's take a look at the data set, then the variables, and then we'll check for any missing values. Our data set. And as you can see, we've got the link below. So if anybody would like to take a look at it, we can send that out. We're looking at the GlowBone Med data set in the Aplore3R library. Our problem statement, what do we want to know? In women 55 years of age or older that have osteoporosis, in a retrospective and observational study, what factors are significant in subject fractures during the 5-year study? Now, what do we have? We have 500 observations and 18 different variables. We have an unbalanced data set, which is 375 no bone fractures and 125 bone fractures. Our variables, the fracture, which is a yes or no categorical variable, is our response variable. Our numerical variables are age, weight, height, BMI, which is body mass index, and frac score. This is a subjective rating of severity of fractures on a scale of 1 through 11. Our categorical variables are rate risk, which is a self-diagnosed risk of fracture as chosen by the subjects at the beginning of the study. MomFrac is where the mother of the subject has a fracture history. Smokers, obviously yes or no. Premeno is premenopausal status at the beginning of the study. Arm assist is whether the subject requires assistance due to arm functionality issues of any kind. Bone med indicates whether the subject was on medication related to bone health at the start of the study, which is yes or no. Bone med follow-up indicates whether the subject was on bone-related medication at a later follow-up point in the study, also a yes or no. And bone treatment, which indicates whether the subject received any treatment related to bone health during the study, and that's a yes or no. And our non-predictive variables are subject ID, the site ID, and the physician ID. We also checked for missing values and found that there were none. So that's a good thing. So let's dig into the EDA. We'll look at our numerical variables and their low S curves, the categorical variables and some bar plots. Back to the numerical variables, we'll take a look at a scatter plot matrix, and we'll look for any multicollinearity issues. We'll take a look also at some of the variable distributions and to check to see if there are any decision boundaries. From these low S curves of the numerical variables, there is a significant relationship between the age, height, and frac score and the chances of subjects having a bone fracture within the 5-year study. There is not enough evidence to suggest there is a trend in the BMI and the weight. These variables may be statistically insignificant in predicting whether the subjects may have a bone fracture within the 5-year study. For the categorical variables, we're looking at the proportion of fracture yes and no for each categorical variable. And as we can see, the proportion of fracture of the premino as well as the smoke are not statistically significant. Scatter plot matrix of our numerical variables show that weight and BMI and age and FRAX score have multicollinearity issues. Further, the same scatter plot matrix, we can see the distributions of the age, weight, BMI, and FRAX score or non-normal distributions. This will be our first indication that LDA may not be the proper method to evaluate this data set. We will also look at the variance-covariance matrix and check for any multicollarity issues. The weight and BMI and age and FRAX score definitely have some multicollarity issues. Multicollinearity issues, that is. The histogram of age shows a right-skewed data set, further indicating that LDA may not be the proper analysis for this data set. Now, these are distributions. These are just counts of the different variables, premenopausal, yes or no, as well as the smokers, non-smokers. And as we can see, these are unbalanced between yes and no. Finally, we'll look at the decision boundaries of age and weight and age and BMI, and we don't see any clear boundaries, further indicating that LDA may not be the correct method. Now I'll hand it over to Mai Dang, and she'll take you through objective 1.
So the first objective for our project is to develop a highly interpretable model enabling us to understand the odds ratio of having a bone fracture in women with osteoporosis. We will employ EDA to guide our approach for fitting the model and use feature selection tools to identify the optimal predictors. Following this, we will analyze the results of our final additive model. For our model fitting approach, it's essential to select a model type that complements our EDA findings, study design, and objectives. Given the fixed response, identify women with osteoporosis who experienced a bone fracture within 5 years of the study, and the predictors collected at the enrollment, age, weight, and bone medication status. Our approach aligns with a retrospective study framework. Considering our moderate sample size, interpreting the odds ratio is an appropriate statistical measure. Bone fracture is binary, indicating an occurrence or absence of a bone fracture, and our primary aims is interpretability, so we plan to train classification models, particularly logistic regression models, using various feature selection tools to identify the most relevant predictors. We will allocate 80% of our dataset for training and the remaining 20% for model validation. To determine the best fitting additive logistic regression model, we will employ 3 metrics: log-logs, AUC or area under the curve, and AIC or Akaike information criterion. The AIC will serve as a benchmark for the model's informational efficiency, with a lower AIC indicating a better model. On the left side is a plot of log-logs versus the predictive probability. The log-logs measures the accuracy of a classifier by penalizing false classifications. Lower log-logs indicate predictions that are closer to the actual class labels, with perfect predictions achieving a log-loss of 0. In other words, lower log-loss equals to more accurate in its predictions. On the right side, we have the AUC or area under the curve. Ranges from 0 to 1, reflects a model's ability to discriminate between classes. An AUC score near 1 implies a high distinction between positive and negative class predictions, while a score near 0.5 suggests no discriminate power. In the example included on the right, Notice that the area under the curve of the GeoMnet model in blue is much larger than the area under the black curve, which is the KNN model. So that makes the GeoMnet model in this example outperform the KNN model. We will train 4 logistic regression models. Notice that since our focus is to build a highly interpretable model, no interaction terms will be included here. The first one is the full model with all predictors except the 3 IDs are removed from the beginning. The custom models fitted with 7 strong predictors that obtained from our EDA. We will also feed 2 more parametric classification models with the predictors selected from the stepwise and the GeoMnet feature selection tool. And here is the result. The p-value of each coefficient tells us whether the predictor is statistically significant or not. Notice that some p-value appear to be significant in all models, like prior fracture, while some predictors are only statistically significant in 1 or 2 models, like age. Let's look at the performance of each model by comparing the metrics. As we mentioned in the previous slide, the lower the log-logs value, the better the model, but the higher the AUC is, the better. If we look at that way, the logistic regression model fitted with the 13 predictors selected by the GeoMnet feature selection tool is the optimal model. It has the lowest log-logs, it had the highest AUC, highest accuracy, but if we look at the AIC, it's the highest among all 4 models, which means this model is more likely to be overfitting. So let's look at the 13 predictors that are fitting into this model. We notice that it has multicollinearity issues, at least between age and FACT score and between the bone medication variables. Similarly, the third model with the age predictors remained from the stepwise feature selection has the lowest AIC, but it still has the multicollinearity. On the other hand, the custom model may not have the lowest log-logs or the highest AUC or even the lowest AIC, but they are not much farther away from the other model's performance metrics. And we know for sure the multicollinearity issue is resolved because that's how we came up with the list of the predictors. You are looking at a plot of the AUC of the 4 model. Notice that the curves are all clustered and overlap each other. We didn't see what we saw in the previous example of AUC, where clearly one model has a significantly larger area under the curve than the others. With not so much of a difference in the performance, we think that the simplest model is the winner here, which is our custom model. Again, it may not have the best performance after all, but we can still optimize it by increasing the complexity instead of adding more predictors. Carlos will dive into it later on, but now we will do a few more tests to double check if our custom model is the best fit. On the left side is a couple of ANOVA tests to compare the models. The ANOVA tests compare the multiple logistic regression models using a likelihood ratio, and the p-value indicates whether there is a statistically significant difference in the fit of the models compared to a baseline model using the first one in a pair. The p-value of the custom one is 0.03, suggests that the custom model may have a better fit than the full model. However, according to another ANOVA test at the bottom left, comparing the custom model and the GeoMnet one, it suggests that the custom model may not be a better fit. Look to the right. This is a Hosmer-Lemmer-Show test or a lack of fit for logistic regression models. The p-value higher than 0.05 indicates that there is no evidence of a poor fit. The custom model with the highest p-value of 0.6 would be considered to have the best fit among the models according to this specific test. So it a little bit contradicts to what we see in the summary and the ANOVA tests on the left. So what I'm trying to say is ANOVA test, Hosmer-Lemmer-Show test can sometimes provide valuable insights about the fit of the model, but they're not the only thing to consider when evaluating the model's performance. Likewise, we can use the feature selection tools and compare all the metrics to find the optimal models, but at the end, we are the one who decide the best model for our dataset based on its EDA. got our winner for the objective 1, which is to find a highly interpretable model. Let's look at the coefficient and the p-value. Only 4 predictors appear to be statistically significant, including age, height, prior fracture, and mum fract. The VIFs looks good, as expected. But if you look at the sensitivity and the specificity, there are huge differences between them. Notice that our positive class is no. The imbalance suggests that while the model is good at catching the no, it misclassifies a large number of not having a bone fracture as having a bone fracture. So we decide to move the threshold to improve the specificity while maintaining the acceptable sensitivity. Based on the ROC curve that we had previously, we decided to drop the threshold to 0.3. The gap now is much smaller. Next, let's look at the summary of the custom model. Keep in mind that these are not the coefficients, as I already converted to the change in the odds ratio. It appears that age and height are not practically significant as opposing to the statistically significant. In other words, keeping other variables fixed, changing the age and height associated with the change in the odds ratio of having a bone fracture in the woman with osteoporosis. But the change is not as significant as the other predictors in the model. The impact of age in the odds ratio of sustaining the bone fracture is notable in women over 55 with osteoporosis. When controlling for other variables, the odds ratio for having a bone fracture within 5 years increased by about 4% for an additional year of age. The 90% confidence interval for this estimate range from 0.5% to 7% indicate that while age is a factor, its practical significance may be limited. Furthermore, family history also plays a significant role. Women with osteoporosis whose mothers had a bone fracture are estimated to have an odds ratio of experiencing a bone fracture that is 116% higher with all other variables held constant. The confidence interval for this estimate is wide, ranging from 8% to 323%, suggesting that this factor is not only statistically significant but also practical importance. Next, Carlos will help increasing the complexity of the model as well as try out with a few non-parametric models to find the best prediction result.
Hello everyone, welcome to the second part of this study focused on predicting osteoporosis and fracture. In this part of the study, we will take a look at the following subjects. First of all, decision boundary, and how important is decision boundary for deciding between our parametric model and non-parametric model. Then, we will build different models, including a complex model. In this one, we will take into account different interaction terms. Another model we will build would be a QDA model, and finally a non-parametric model based on random forest. On top of that, we will examine the most important metrics to measure the performance of the model. And finally, we will compare these models using these metrics. We will discover which model is better based on these factors. Now, let's take a look at the decision boundary. Decision boundaries are used to delineate the boundaries of classes in a classification algorithm. In general, we can say that there are two types of decision boundary, linear and nonlinear. Parametric models, for example, perform very well when we have a linear decision boundary like a vertical line, or even a decision boundary that is made up of perpendicular zigzags. However, when it comes to a non-linear decision boundary like the one displayed here, parametric models don't tend to perform well. However, non-parametric models, such as random forest or KNN, will be highly effective. In our EDA analysis, we determined that age and height are two strong predictors. It seems the decision boundary between age and height for fracture classification is not linear. The visual inspection suggests that a non-parametric model seems to be more suitable for predicting fracture. In this part, we will explore the decision boundary of different models for our data set. We believe that the decision boundary analysis will lay out part of the foundations for the selection for our final model. On the first plot, we are seeing the relationship between age, height, and fracture. On the second image, we can notice the decision boundary built by an LDA model is not very effective because there are substantial number of observations of both classes, fracture and not fracture, in both sides of the boundary. Moving on, a QDA model offers more flexibility in terms of a more exotic decision boundary. However, it is not able to delineate both classes effectively. Finally, on the last picture, we are displaying the results of a random forest. We can notice that random forest, a non-parametric model, is more optimal, and it is really able to delineate both classes with highly effectiveness. So, in general, according to the visual information, a non-parametric model would be more suitable for our final classifier. Now, let's explore the different metrics we would use to measure the performance of our models. First, accuracy. Accuracy is the number of correct assessments divided by the number of assessments. Sensitivity. Sensitivity in this case would be the proportion of women predicted not being fractured but that are not fractured. Specificity, on the contrary, would be the proportion of women predicted being fractured that are really fractured. Okay, let's move on. PPV, positive predicted value. It would be the odds of being fractured given one woman is really fractured. It mainly focuses on the probability of being fractured or not if the test is positive or negative. MPV is the opposite. It would be the odds of not having the disease given one woman doesn't have the disease. And finally, prevalence. Prevalence would be the proportion of the population that is affected by a particular disease at a given time. For example, if 75 women don't have the disease out of 100, then the prevalence would be 75. Moving forward, log loss is the indicative of how close the prediction probability is to the corresponding actual value. AUC, on the other side, is an indicative of the degree of separability between both classes. It is really important to take into consideration both metrics because a decline in the log-log score doesn't necessarily mean a change in the AUC score. The classification threshold in a statistic is a boundary to assign a specific predicted class for each object according to the probability. In this problem, there are two important factors why we would like to move this threshold. One factor is that one of the classes is in balance, and using 0.5 as a threshold would lead to poor classification. And the other is that the minority class is very important, and we would like to predict whether a woman is being fractured if the probability is below 0.5. Now we are ready for diving into the exploration and comparison journey of the different following models. A simple model based on multiple logistic regression, a complex model based on a multiple logistic regression but including interaction terms, an alternative models based on QDA, and finally a non-parametric models using random forest. Here we can see the results of the simple model we fed in part 1. We can visualize the different predictors and measures to evaluate the model. You can pause the video and take a look with more detail. The idea is that we will compare these results with the results of the other models. Now we will set the foundations for building our complex model using interaction terms. The visual information suggests that it seems that there's evidence of an interaction term between age and prior fract because they are not trending in the same direction. There's a downward trend in the case of prior fract equals yes. However, there's an upward trend in case of prior equals no. So, for these reasons, we will take into consideration age and prior fract as interaction terms in our complex model. Now let's explore monfract and R-assist. There's evidence that monfract and R-assist are interacting together because when monfract equals no, we will have a different proportion of diseases for both categories of assist. So as a result, we will consider both predictors as interacting together in our complex model. Moving forward, in this part, we are presenting the analysis of other interaction terms we discarded. You are very welcome to check these slides with more detail. Nevertheless, the visual information suggests that there's not interaction terms for these scenarios because they are pretty much trending in the same direction. That's why we laser focus on the stronger predictors for this analysis, including age, height, prior fract, fract, and assist. Now we can see the results of the complex model with the interaction terms that we took into account. As you can see from the image, the results of the complex model are very similar to the simple model. However, I should say that in terms of accuracy and sensitivity, the simple model is more effective. However, we will take a look into more detail at the end of the presentation. Okay, moving on. Now we are presenting the results of the QDA model. As we can notice from the results, this is the worst model that we have reviewed up to this point in terms of accuracy, sensitivity, specificity, AUC, and log loss. Random forest. We have decided to use random forest as a non-parametric model because it uses banking, it has feature selection incorporated, and more importantly, random forest is highly effective for both categorical and numerical data. This is of course a limitation of K&M. We believe that random forest will be one of the potential models for dealing with this problem because, as we have mentioned before, the decision boundary of this problem suggests that a non-parametric model would be more appropriate for it. In the right side of the slide, we can also visualize the results of the model and the variable importance. As you can see in the results of the variable importance, this is in alignment with our EDA analysis and our important predictors, with the exception of BMI and weight. This is something we will touch at the end of the presentation. Now we are ready to visualize the results of the random forest model. If we take a look at the important metrics to measure the performance of the model, they are very close to the simple model and complex model. We believe that these three models will be the final competitors for our final model. We think that QDA will be discarded because this model is not effective as the other three ones. In this graph, we can visualize the tree built by the random forest model and the different predictors that the model took into consideration. Another important element when it comes to model comparison in terms of classifier is the IUC plot. As we can notice from the graph, the simple model, random forest, and the complex model, they cover more area than the rest of the models. Finally, the decision boundary again. We believe that the decision boundary will play an important role for the final decision of our final model. Now we will pick our final model based on the listed measures. The first model we will discard will be the QDA model. As you can see from the image, in terms of the metrics listed here in the table, the model is the worst. In the same vein, the simple model and complex model, they are very close in terms of these metrics. If we didn't have random forest here, to be honest, we would choose the simple model because it is more simplistic, there would be less complexity, and pretty much we have the same accuracy. But we have random forest. So finally, we would choose random forest over all models because all the important metrics are very close. And more importantly, the fact that the decision boundary between age and height doesn't have a clear division between both classes, a non-parametric model would be the wisest decision here.
In conclusion, this project was firmly centered on achieving two primary objectives: the construction of highly interpretable model and an optimal model for predicting bone fracture risk in women over 55 with osteoporosis. Our first objective focused on understanding the relationship between the predictor variables and the likelihood of bone fractures within a 5-year time frame. The interpretation provides insights into the factors that contribute significantly to the fracture risk. For the second objective, after throughout evaluation, the random forest model emerged as the most effective predictive model. This model outperformed others in terms of accuracy, yet it presents a challenge. The predictor importance that we obtained from the decision tree did not align with our initial exploratory data analysis, or EDA. Going forward, there are clear avenues for enhancements. One potential improvement involves retraining the model to incorporate body mass index (BMI) as a predictor. Additionally, expanding the sample size could further validate the model's predictions and possibly reveal subtler associations between the predictors and the fracture risk. Experimenting with model parameters and structures may also yield a more optimal predictive model.